Hey, what up, players? Today we're going to take a look at the last new section, or at least we'll start the last new section on Taylor polynomials. It's a big section. It's something we're going to spend a lot of time on, probably today, tomorrow, maybe into Thursday before we get done with it, but we'll see how it goes.
So Taylor and Maclaurin series. Taylor series is the broader name of this chapter. A Maclaurin series is just a specific type of Taylor series. We'll see a little bit more on that later. But the basic idea goes like this. On the screen right now, you see the graph of an inverse tangent function. And for whatever reason, we are going to approximate what the shape of this curve looks like using a power series, which are useful for computers and programming because they're simpler. It's just a big polynomial, and the number of terms of the polynomial depends on how specific we want to get. And so if I want a polynomial, and I'll show you, this series over here looks crazy complicated, but it's just me putting this into sigma notation, so I'll be able to do this quickly and easily. If I want to do a Taylor series that is an approximation for this curve around x equals 0. First, I would say, well, I need it to be equal to whatever the value of the inverse tangent is at 0, and we can see from the graph that is 0. So right now I've got well, I suppose this is a 0-degree Taylor series polynomial. It's just y equals 0. And if I zoom in around x equals 0, it's a great approximation at 0, but it's completely garbage outside of that. So I can get a better approximation by doing what we have been doing for a lot of the year. I'll do a first degree Taylor series approximation, which we've been doing for a long time. It's called the linear approximation. It has the same value at x equals 0 and the same slope. In this case, it's just the equation y equals 1 plus x. The slope is equal to 1. The value of the function is equal to 0. And now when I zoom in on 0, I can see it's a pretty good approximation at 0 and around 0. Now, when I move farther and farther away, it's a terrible approximation, but at least around 0, it's pretty good. The idea of Taylor series and Maclaurin series is that I'm not just going to have the same value and first derivative. I want to have the same second derivative, which I can do by increasing to a second degree. And so now the same value, the same slope, and the same curvature. And as I add higher and higher power to this series, this is a third degree, fourth degree, fifth degree, sixth degree. And as I go more and more and more, we can see that the fit gets better and better and better. But in the case of this one, like we've seen with some of our other series, looks like my interval of convergence is only between -1 and 1. I'll go through this again, starting with the 0 degree and go fairly quickly through this. You can see those flip-flopping on the sides, and it's getting better and better and better, but only to a certain point. Visually, it looks like it's from -1 to 1. So that's what we're going to be doing, except with a different function. We are going to be taking a look at the function e to the x. I chose e to the x because, frankly, it's an easy function to differentiate and evaluate. We'll do this one centered at 0. I think we'll just focus on 0 today and then move on from there tomorrow. But with this function, e to the x, the reason that I'm choosing e to the x is because the derivative is e to the x, and the second derivative is e to the x, and the third and the fourth, and every derivative of this function is e to the x. And so if I want it to have the same value, the same derivative, the same second, third, fourth derivative at x equals 0, I'm just plugging that in for this function. E to the x evaluated at 0, its derivative evaluated at 0, the second derivative evaluated at 0, et cetera, et cetera, et cetera. These are all 1. This is going to make this process go pretty easily. So to start this process, we'll start by taking a look at, if I want to do a fourth degree approximation, I'll start with the fourth derivative. The fourth derivative, of course, is e to the x, and at x equals 0, the fourth derivative is equal to 1.
Our fourth derivative needs to be equal to 1, and so we'll just come up with a nice easy function that is equal to 1, no matter what the value of x is. It needs to be at 0. this one is equal to 1 everywhere, so it's about as simple of a function as we're going to come up with. If this is the fourth derivative, then our third derivative will be the antiderivative, or maybe I should say an antiderivative of 1. And so, of course, the antiderivative of 1 would be x plus something. But of course, when I plug 0 into this, I need it to be equal to 1. All of my derivatives need to be equal to 1. And so since g triple prime of 0 needs to be 1, that means our value of c is 1, and our third derivative ends up being x plus 1. Well, if that's what our third derivative is, then our second derivative will be an antiderivative of that. Antiderivative of x, x squared over 2, antiderivative of 1x, and then my usual plus c. Same idea here. The second derivative of e to the x at 0 would be equal to 1, which means my value of c is once again 1. That's why we're doing e to the x. Lots of repetition, lots of easy calculations for our different constants. So our second derivative is x squared over 2 plus x plus 1. And if that is our second derivative, then our first derivative will be an antiderivative of that. Antiderivative of x squared over 2 would be x cubed over 6 plus x squared over 2 plus x plus some constant, but at this point I'm noticing what the pattern is. The first derivative is going to have to be equal to 1, which means this one will have to be equal to 1 as well. This will get a little bit more complicated when we get to more complicated functions. And I'm also going to maybe point out that that 6 came from 3 times 2. For reasons that we'll find out in just a moment. If this is our first derivative, then here we go. We know what our function is. Our function must be an antiderivative of our derivative. And so let's see, an antiderivative of x cubed over 3 must be x to the 4th over, well, 4 times 3 times 2. And this time I'll leave it like that. In fact, I'll even say times 1. We're going to establish a pattern at this point. The antiderivative of x squared over 2 is x cubed over 3 times 2. I'll add the times 1 plus x squared. And it's, of course, x squared over 2, but I'm going to call this 2 times 1. Sorry about that. And then the antiderivative of 1 is x to the 1st over 1. And then I've got 1 at the end. My plus c will end up being a plus 1 because, well, the same reason it was for all of the other ones. And so we'll have 1, but I'm going to call this x to the 0 over 0 factorial to fit in with the rest of the patterns. So what we're seeing here is a 4th degree Taylor series for e to the x. And we're going to head over to Desmos and see what this looks like.
All right, so we are looking at the graph of e to the x right now. And so I will just put the terms that we just found so we can see what it looks like. And I'm going to go through them one at a time again so we can see the different degree approximations. First order approximation is that the function is equal to 1, and it looks great at x equals 0, but everywhere else, not so good. Add on the x term, and now we've got a linear approximation, which is a better fit around 0. I suppose I can zoom in on this one and see that around 0, everything's looking pretty good, but it starts to diverge away from that down the road. Add the next term, x squared over 2. We see that it gets to be a better, looks like definitely between 0.5 and negative 0.5, looking pretty good. Add on the next term, x cubed over 3 factorial. Now we're all the way out, looks like from negative 1 to 1, looking pretty good. And then as I go farther and farther down the road, x to the 4th over 4 factorial, we're extending past x equals 1. And in fact, if I add on another term, you could guess that the next term is going to be x to the 5th divided by 5 factorial. And it gets better and better and better. Every degree of the approximation makes it look better and better and better, which is a good thing. And this brings us to the general form. So here is the general form for a Maclaurin series. We'll focus on this today. That's what we have been focusing on. The key thing here is that everything's happening at 0. This looks nasty, this looks ugly, but this is actually what we just did with e to the x. It's the sum. This is just a big, crazy coefficient. We saw where this n factorial comes from taking antiderivatives. We've got x to some power. And then this just says the nth derivative, whether it's the value of the function for the 0th derivative, first derivative, second, third, fourth, et cetera, et cetera, et cetera. Go ahead and get that copy down. Pause if you need to. But when we go back and look at what we did for e to the x, it was 1 plus 1 times x plus 1 times x squared over 2 factorial. The derivative was just 1 for everything along the way. So 1 plus x squared over 2 plus x cubed over 3 plus x to the 4th over 4 factorial, and it just carried along. I'd like to finish today by looking at another function that we're familiar with, the sine function, except instead of going through and doing this with antiderivatives, I'd like to just plug the numbers into the formula where I've got something times x to the n power over n factorial, and we know the values of all the derivatives of sine. And so the 0th derivative, the value of sine, and we're doing this specifically at x equals 0. We'll take a look at Taylor series and series not centered at 0 tomorrow. But sine of 0 is 0. So my first term is just 0. That'll go away. The next coefficient is the derivative, or excuse me, the value of the derivative of sine at x equals 0. Well, the derivative of sine is cosine. Cosine of 0 is 1. And so there's our coefficient there. The next derivative of sine, the second derivative of sine, is negative sine. Negative sine of 0 is 0. And then we go to the third derivative. The third derivative is negative cosine. Negative cosine of 0 is negative 1. And then we're back to where we started. Sine function, once you get to the fourth derivative, you're back to where you started. The fourth derivative of sine is sine. And so its derivative is 0. And then we've got the same pattern going. We're going to have 0, then 1, then 0, then negative 1, then 0, then 1. The next term would be 0, and the term after that's going to be negative 1. So if I get rid of my 0 terms, sine of x is approximately, our Taylor series, or Maclaurin series in this case, representation is, oops, I'm going to call that just x, 1 times x minus x cubed over 3 factorial plus 0 plus 1 x to the 5th over 5 factorial. Oops, I forgot the factorial on that 3. I'll go back and put that in there. Not just 3, but 3 factorial. Then the next term would be 0. The first term I don't have written down here would be the 6th term, but if I look at what the pattern is, 0, 1, 0, negative 1, 0, 1, 0, the next one's going to be negative 1. So negative 1, x to the, we would be at the 7th derivative by that point, over 7 factorial, plus a 0 term for the 8th derivative, plus a positive x to the 9th over 9 factorial, and I'm running out of space. Oh, I did it again. I forgot the factorial. Let's make that 9 factorial and 7 factorial. I'm going to switch to ellipses and say, I think we've established a pattern. And you can go ahead and graph this on a graphing calculator and take a look at how well this fits a sine function. Make sure your calculator's in radian mode for this one. What I would like you guys to do between now and tomorrow, I assume you're watching this on Monday, so tomorrow would be Tuesday. And so before you come back tomorrow, certainly take a look at the homework assignment. You may not be able to finish it, but take a look at the section, take a look at the formulas. But I'd like you to try to do what we just did here with sine. I'd like you to do this with cosine. I'd like you to come up with a Maclaurin series approximation for the cosine function. We will gosh, maybe we can finish this one up tomorrow. We'll see how things go, how if you guys have questions or anything like that. But we need to take a look at when it's not centered at 0. We'll call that a Taylor series. Take a look at some examples and get this thing wrapped up. But that is all I have for today. So I will see you on the message boards or see you online or see you in my email or wherever I see you. All right. Have a good day.